The foundation of our physical reality is governed by an equation that does not actually describe anything physical. The time-dependent Schrödinger equation is the fundamental equation of motion for quantum mechanics. But built directly into the structure of this equation, right next to Planck's constant, is the imaginary unit I. In classical mechanics, Newtonian equations calculate deterministic, real-world vectors. You input your variables, and the math hands you back a precise position or a defined momentum. Schrödinger's equation outputs a complex wave function. You cannot map this output directly to a physical measurement because physical instruments cannot measure imaginary numbers. The wave function, psi, is not a wave of matter. It is not a wave of energy, nor is it propagating through any physical medium. It is a pure computational device. Because of this, quantum mechanics was functionally incomplete as a physical theory. It required a mathematical bridge to translate this imaginary amplitude into an observable reality. By 1926, physicists had a highly predictive wave equation, but zero consensus on what the resulting wave actually represented. German physicist Max Born decided to ground this abstract math by applying it to a concrete physical process. He chose a highly specific problem, calculating the interaction between a free particle, an electron, and a target atom. A scattering collision is the perfect test case. It forces the wave mechanics framework to yield a definitive outcome, a trajectory that could theoretically be detected by instruments in a lab. Born used the Schrödinger formulation because the competing matrix mechanics could not easily handle the asymptotic behavior of particles traveling inward from infinity. He did not set out to invent quantum indeterminism. He simply wanted to mathematically predict exactly where an electron would go after bouncing off an atom. In his pivotal 1926 paper on the quantum mechanics of collisions, Born outlines his attack on the problem of free particle interaction. He starts by assuming the incoming unperturbed electron can be mathematically modeled as a continuous manifold of plane waves arriving from infinity. The boundary condition occurs when this plane wave strikes the potential energy field of the target atom. This interaction immediately transforms the simple, straight-line path of the electron into a complex diffraction problem. The resulting scattered wave radiates outward, containing a broad spectrum of new possible states for the electron. While the Schrödinger equation successfully models the interaction, the output remains a smeared continuous wave function. It does not yield a single deflected particle. By treating the electron strictly as a wave, the interaction naturally produces a superposition of all possible unperturbed states. The classical expectation of a single, defined trajectory breaks down entirely. Looking at Born's mathematical solution for the scattered wave evaluated at infinity, we find an integral equation. Born interpreted the yield function, denoted by phi, not as a causal coordinate, but as the likelihood of the electron being thrown out at a specific angle with a specific change in energy. He formalizes the relationship between this abstract yield function and observable probability in a footnote added in proof, noting that the probability is proportional to the square of the quantity. In modern mathematical terms, squaring the amplitude requires multiplying the complex wave function by its complex conjugate. When you perform this multiplication, the I² terms resolve to -1. The imaginary elements cancel out entirely. You are left with a real, positive number. This mathematical step is mandatory because a physical probability must be a real, positive value to make sense in the real world. Born traced this intellectual leap back to Albert Einstein's earlier work on the photoelectric effect. Einstein interpreted the square of an optical wave's amplitude as the probability density for the occurrence of photons. Born adapted this logic directly to matter waves. Born proved that the wave function's squared amplitude is not a measure of physical intensity. It is the exact statistical probability of finding the particle. What originated as a highly specific solution for electron collisions quickly evolved into a universal axiom applied to all quantum systems. This chart shows a standard one-dimensional probability density function. The peaks represent the highest probability of finding the particle, while the troughs represent the lowest. The probability of finding the particle within any specific interval is calculated by taking the area under the curve. This introduces a strict mathematical constraint required for the model to function: normalization. Because a particle must absolutely exist somewhere in the universe, the integral of this probability density over all of space must equal exactly 1, or 100%. Normalization enforces a strict mathematical boundary. Any formal solution to the Schrödinger equation that cannot be normalized is physically meaningless. The Born rule also mathematically dictates one of the strangest phenomena in physics, quantum interference. In classical physics, probabilities simply add together. In quantum mechanics, states are added in superposition first, then the Born rule is applied. Squaring that combined amplitude generates extra mathematical cross-terms. These exact cross-terms cause the probability wave to destructively and constructively interfere. Without the Born rule's requirement to square complex amplitudes, these interference patterns cannot be mathematically justified. Returning to Max Born's paper, we find the ultimate philosophical consequence of this rule stated plainly in the text. Here, the whole problem of determinism comes up. Born concludes that there is no quantity that causally fixes the consequence of the collision. Determinism in the world of atoms must be abandoned. The Born rule forces us to accept that the clockwork universe is dead, and that nature's foundational language is inescapably probabilistic.